What's up? Let's go. We're back. I'm Tui, and let's get back into Tui Time graphics. So last time we are now drawing a triangle and scaling it on the screen utilizing this 4x4 matrix, and let's dive into what the hell this means. So now that we're scaling, we want to apply a couple other transformations such as transform, which I'm just going to go into this. I made this little drawing so that I can explain it a little bit better. Okay, so when you're drawing say a triangle on the screen and you want to move it, well, so you have your object, whatever it is. This is a giant coffee cup and it's rendered on your screen, and you want to draw these vertices and move them around in the world. Well, you have your initial vertex position. So these little red dots are going to represent the initial vertex position. They're not actually 2, 3, 1, 1, but this right here would be X, this would be Y, this would be Z, and this is just like the W component that I might talk about a little bit later. Basically, what this allows us to do is multiply our initial vertex, so say this is right here, times this transformation, this transform matrix, so whatever it is, it could be to move it or rotate it or scale it. This vertex right here, this point, we're going to transform that point and output the new position. In this case, this is the identity matrix, so it just means it's 1. So we're multiplying the vertex position times here, and it will move to the exact same spot. So we're going to go through all of these vertexes, multiply every single one by this transform matrix, and they're going to move together. So we can move this entire triangle and not have to worry about this point moving off into random space. They move together. This triangle will move together, and so that's where this transform matrix comes into play. So let's go down here. If anyone's heard of linear combinations, this is going to come in handy. So basically, our model, our triangle, is what we're going to refer to it as a model. Okay, as a model, because this model will hold the vertex points and points on the graph. So we have 3 different types of translation, or 3 different types of transformations we're going to do on our so this is a transform matrix. We have 3 different types that I'm going to at least go over today. There's more, but on our model, and that is translation, rotation, and scaling. And so how we do these is these will all be multiplied together, and then once these are all multiplied together, we can multiply every vertice by this final matrix, because these create a linear combination of matrices, which will output, like I said, this is 1 times 1 times 1. These could be whatever you want. This translation matrix, which will move the triangle on the Cartesian graph. The rotation will rotate the triangle on the Cartesian graph, and the scale matrix will make it bigger or smaller. Once we multiply this one by the rotation matrix, and these two by the combined by the scale matrix, we'll output another 4x4 matrix that then we can apply this vector times. So here's our original vector. Here's all of these combined. Multiply this by this by this, we'll get another 4x4. That will become our transform matrix, and then the vertex positions will then output into another vector that we can then plot on the screen. That's why it's so nice to use these matrices in graphics, because we can do things like this really easily and move it around in 3-dimensional space, and the GPU is really good at doing multiplication like this. So it's actually optimized to do that. And so that's what I'm going to be doing there. Here, so this is just like, say, the translation matrix. So to create the translation matrix, the rotation matrix, and the scale matrix, we have to apply certain formulae on it. So the translation will be right here. So say we want to translate. Well, we'd have our x, y, z, our x, y, z, w vector, and we pass that in, and then we translate it using this exact. So this is the translate. So how far do we want to translate it in the x position? So if we have our graph and here's x right here, here's y. Well, how far do we want it? We want to translate it right here. Well, we want to translate x and by this amount. Wow, that's really thick. Whatever. We want to do x by that amount, and then y would be by, this amount. And then z would be whatever z is, which is like that amount. And then, so transform by x, or translate by x, translate by y, translate by z. And then that will output at least the translation of the x prime, which is like what the x becomes, the y prime and the z prime. So that's translation. Rotation is exactly the same type of thinking, whereas you input x and y and z, and then see, we don't use the w yet, but you input the x, y, z, you get this rotation out, and then you multiply the translation by the rotation, and then you do the scale, where you scale by x, scale by y, scale by z, and you output a new. We've already done scale, but that's the idea. So this represents our model transform, our model coordinates, our world coordinates. So our model coordinates are wherever they start. So this right here, these are our model coordinates. This is just where it starts. This is from nothing, and then we're going to put those into world coordinates by applying these three different transform matrices. And so and then we'll get into perspective and orthographic. I don't know why that says projection. Orthographic projection, that doesn't make any sense. This is supposed to say perspective. I'm going to actually change that. Perspective. Perspective projection, and then sorry. But don't worry about this yet. Anyway, back on topic. We have translation, rotation, and scale. So what we're going to do is we're going to apply those inside of our project. So I'm going to figure out the best way to do this. I don't know the best way to do this. Translation. I'm going to put you right here. I'm going to zoom out. And then I'm going to put him off in the corner. Nobody puts baby in the corner. Right there. And then I'll shrink him. So translation. So just like we did scale, we're going to copy that. And then we're going to be basically just doing the translation matrix. And then we'll be multiplying them together. The order in which you do multiply them together matters, so we'll have to focus on that in a little bit, but let's translate. So instead of scale, we're going to translate the model in which axis. So basically this is the direction axis, but I'm just going to call it direction to make it a little more clear, and then we're going to have to put that there. So we have our X, Y, and Z, and then as you can see, it's very easy to output the translate. And we'll go and test this real quick. So we have our translate by X, Y, and Z. Now, keep in mind, so this is columns. So this is column 1, this is column 2, this is column 3, column 4. So really, we should rotate this and realize that column 1 would be here, so the translation for X would be right here. Y would be right here at the end of the column, and then Z would be right here at the end of this column, you see. So then we're going to multiply whatever we have right now for ourselves times the result. And so if we had scaled ourselves already, well, we'll have that 4x4 matrix, that float 4x4 matrix, and then we're going to multiply whatever we got from that times this translation, and then we'll get a new matrice to define where our vertex points are going to be multiplied by. So let's go ahead and go back to our basic scene and only draw one triangle. We're going to draw triangle 1. So we're still going to scale it. See, so I put this in order, so you're supposed to translate, rotate, then scale. So we'll translate triangle 1 dot translate. Oh, got to add it, I guess, to the primitive. We're gonna switch the way this operates in the future. By the way, I just want to kind of get this stuff working. Translate axis. This is direction. And this is direction. Direction. I could have just copied these. And then translate. So we're going to multiply. We're going to translate whatever we have for our model constants. And so yeah, so let's do this. So triangle 1 dot translate. What direction? So float 3 x, y, z. We're going to translate by 0.5 in the x direction, 0.5 in the y direction, and we're not going to translate. Actually, you know what? We're going to do in the x position, and then we got to apply this transformation to like this. So we got a 0. No, wait, I think we'll just do 0.5. So we're going to go x, y, and then that's going to output our new position. Translate 0.5, 0.5. So just like we did our scale, where we moved our all the vertices, we're going to also translate up from the center here, up 0.5. So now you see that we're now translating very easily using this. So yes, now that that's done, we can now get into rotation. So these say translate, rotate, scale. So right here we want to be able to call triangle 1 dot rotate, and then you're going to rotate. Basically, you want to rotate around the points on a graph. So if we have our x and our y, oh, that was bad. Our x and our y. Let's say we want to rotate. Well, which direction do you want to rotate? You can rotate an object in 3D space real easily. Like this coaster right here can rotate this direction or this direction or this direction. We're rotating all different. And basically what you're going to be telling it is which axis to rotate around. So if it's the x, it would be the horizontal, and it would rotate around the x. If it was the y, it would be vertical, so it would be rotating this way. And z would be rotating around the z, which comes right at your face, and just like so. So that's why we're going to be passing in the axis in which it rotates around and the angle. So we're going to want to rotate around an angle of whatever. So, and then that's going to be in radians. No, it's not. This is going to be, no, not, it's going to be in degrees for sure. So 45 degrees. And then we're going to want to pass in the axis in which it's rotating, which will be a float 3. And that's which axis. So 1, 0. Like you just have to state which one it is. And then, yeah, but we don't have that yet. It doesn't exist. We're going to have to go to our mask and create it. So I'm going to copy scale. And the rotate one takes a second. So what I'm going to do is reorganize this. Let's get this guy centered right there so we can read from it and make it easier. Now remember, this is columns, so we're going to have to organize this a little bit different. So rotation will be not scale, we need to rotate. And we have our XYZ, that's fine, but we also need an angle, and that's going to be a float. We're going to rotate around an axis at an angle. So we have our XYZ. The C you see is cosine of theta, so cosine of the angle. So we can say let C as a float equal the cosine. Yes, it's cosine of angle. And then let sine float equal the sine of the angle. You'll notice that every single one of these has this 1 minus c, so I'm just going to name that MC, like minus c, 1 minus c, MC. Equal 1 minus c. And yes, the way I like to kind of, I know this is a lot of data, but it's easier to read if you do it this way, so I'm going to do that. I'm going to call this column, so we're going to create column 1, row 1, or well, row 1, column 1. And then so since this is row, this will basically be column 1 still, but row 2, column 2. So we're going to create all those variables real quick. R1, column 1, float equals 0. And I'll just set those equal to 0.0 first. And then row. So this will be column 1, 3, 4. Then I'm going to copy this 3 more times. Oh. Boom. I know this is a lot of memory that we're using, but it's easier to visualize, and we can always copy and paste later. Change all these to 2, so now this is column 2, column 3, column 4, column 4, and so now we have row 1, column. So these shouldn't actually have any errors, but they are not being used. So let's just kind of use them real quick. So this will be, this is column 1. So row 3, column 1, row 3, column 1. This is row 4, column 1. And then I'm just going to copy this. And like I said, this is purely for legibility, because we're going to be going from row, or from, you know, this, looking, because we're in column major, this is row major. This looks like column major. So, yes. Make sure row 4, column 1. Okay, now we just need to go, this is column 2, column 2, column, or 3, 4, and the same thing. 2, 3, 4, 2, 3, 4, 2, 3, 4. Column 1, column 2, column 3, column 4. Okay, so now that we have these in place and all these little errors should go away, we can now do this rotation formula just like it says. So row 1, column 1 will be x squared, so x times MC. Okay, that was easy. Plus C. Next we'll do for row 2, column 1. See, we're in row 2, column 1, so we're going down, but we're going, in this case, we're going kind of across. So row 2, column 1 would be right there. So we go x times y times MC plus z times s, x times z times mc minus y times s, and then we have 0. Okay, so you'll notice that there's this pattern of x's here, x, y, z, that will continue, and then when it does the x squared, it always just adds c, and these other ones are kind of mixed up a little bit, so there's not really a pattern to memorizing those that I have found. But let's do the same thing for row 1, column 2. So this is going to be x times y times mc minus z times s. Now I'm going to go ahead and invert these because y times x times mc, because that's the way it's going to be, x, y, z, and I'm just going to kind of follow that pattern. So y times mc plus c, y times z times mc plus x times s. See, so x, y, z. Now we're going to do the same thing as z, z, z. And then there's 0, so we go x times, well, z times x times mc plus y times s, y times z, gosh darn it, z times y times mc minus x times s, z times mc plus c, and then you have your just 0, 0, 0, 1 for this final one. It looks like I'm not even using this. Probably should do that, huh? Column 3, column 4. I didn't do that. Okay. So now that that's all laid out, and we have 0, 0, 0, 1, 0, 0, 0, 1, we can utilize this rotate. That wasn't so bad. You can find this online, by the way. This is on just Google. Google any one of these rotation, transformation, scale transformation. They'll all come up fairly easily. And like I said, we do translate, rotate, scale. So we'll translate, rotate, scale. I need to add this rotate function to the primitive. I'm just going to copy this. Rotate by the angle, which is going to be a float, and then we're going to rotate by angle, which is angle, and then this will be direct. Oh, this will be axis. And delete this stuff. And then we don't need direction, we just need axis. And yes, so now go back to our basic scene. You'll see triangle.rotate works, and so we're rotating 45-degree angles along the x-axis. We're not going to do the x-axis. We're going to want to do the z, so it rotates this way because we're only working in 2 dimensions right now. And so this will be the z right here. And everybody should be happy. Rotate axis. What are you doing? Did I misspell it? Triangle. All right, so now we're going to be rotating along the z, 45 degrees. Maybe. Yep. You'll see it doesn't maintain its shape. It kind of warps a little bit, but that's just because of how we're projecting it. We'll fix that in the future because it just has to do with our projection. So yeah, now we're translating, rotating, and scaling. Awesome. What I'm going to do is I'm going to make it so we can visualize this so it looks a little bit cleaner. We're going to just go over, well, func render, command encoder, mtl render, command encoder. Then we're going to take in the delta time, and so now I'm going to update the rotation with the delta time so that it updates. We're going to want to do whatever we want to do, and then we're going to call super.render with mtl render command encoder. Well, it's just a command encoder. Okay, So now, since I want to rotate by the delta time, I'm just going to put this right here. And then I'm just going to call delta time. Now, where are we calling this? We're calling this from the render. We're calling scene.render. So here, you'll notice that we have a view, and our view has something called the preferred frame rates per second. And so it's set to 60 right now. So if we go let delta time equal 1 divided by, this is going to need to be casted as a float, and then we're going to say view dot preferred frames per second. That's going to be 1 over 60, so it's going to be 1/60th of a second. This will be updating in real time rather than computer time, which is insanely fast. This will be doing real time update of a position, and then we can pass that in to delta time as delta time. Now we're probably going to get some errors we're going to need to fix. Triangle 1 needs to be global. And remember, we can add. So in init, we added our triangle. So we can have some sort of a constructor for all the things in our scene. But I'm just going to go like this. This is going to be triangle, and then we'll just say, I'm going to call this T, makes it easier. T, 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 T. So now T needs to be initialized first since it's there, so we're just going to move him up there, and T equals that. There we go. Is everybody happy on here? No. This has extra thing, so we're gonna need to, since scene is a node, I believe that our node might need it. So nope. Okay, so let's go ahead and try to press play and see exactly what happens. Oh, okay, so I thought so. Delta time and call. It's wondering what the hell delta time is because we're calling it on the node. So our scene right here needs to have let's just go down to the node class and add it on here. So command encoder, delta time, everything will need to basically update with delta time. So float, and then we're going to want to just go delta time, easy enough. Basic scene, render with delta time. So overrides. Press play here. Oh gee whiz. In our primitive class we didn't update this to update with delta time. That's okay. Render, this overrides. So we don't necessarily need to do that. We just need to go delta time. I'm trying to think, should I even do it here? Yes. Delta time, command encoder. It's a good thing we're implementing this because we're going to need it in the future. Let's press play. Now it's coming all the way down. Oh, it's wondering what the hell delta time is. That's going to need to be a float. Let's press play. See if we get a build succeeded, and we should be rotating around the z-axis, just like so. Remember, we translated it, and now we're rotating it around. This point is our is now our origin, because we moved our origin for the model into world space, but our model's right here. So this is where the new origin actually is. Origin used to be here, but we translated it to over here. So yeah, now that we're rotating, let's just make it look a little nicer. So for the future, we're going to get rid of this translate. And the scale we can keep. It's kind of nice to have the scale because it makes it smaller, it doesn't make it a huge triangle. And yeah, see, let's scale it a little bit more. Yep, so now we're rotating right here. Just the way we're projecting it makes it look kind of funky. It kind of elongates at the top a little bit, but we will fix that. Trying to, interesting. Okay, so our red triangle. The next thing we can do is, so I want to show you. So we're rotating right now currently around the z-axis, but what do you think would happen if I rotated around the, let's say, x-axis? So we're going from rotating around the z-axis, coming right at you, to the x-axis. So we'll be doing this. What do you think will happen? Keep in mind we haven't put depth in, so there's no depth, and there is no projection, so it's not pushed back into space. Currently it lies on the 0 of z. And so what do you think would happen if we rotated around the x? Think about that. Pause it, I don't know. Do what you do, but I just want to go ahead and rotate around the x-axis now. And let's observe what does happen. Okay. Oh, okay, so that's interesting. We have a little triangle, then we have the top of a triangle. Okay, so if you've never done this before, it's kind of, you might not know what's going on, but basically what's happening is we'll see the top of the triangle, it will come around, and then it will go back into depth, and then the top of the triangle is coming up now, and now you see it's just kind of rotating around the x-axis, but once it gets behind 0, since we haven't told the GPU what depth is, it doesn't know what to render back here, so it's not going to render back there. So what we're going to do next is we're going to implement depth so that we can, make this look like it's actually rotating along the x-axis in space in 3 dimensions. So let's do that by talking a little bit about the depth buffer. I didn't create anything, but basically what the depth buffer is it is this giant, oh man, I should have prepared something for you, but pretend this is your screen, and it is made up of, I don't know, let's just make it simple, 4 pixels. You have a giant screen, and it's made up of 4 pixels, and each one of these spaces right here, let's I don't know. Sorry, I'm trying to figure out the best way to do this. Okay, I'll just do it like this. So say your screen is made up of 4 pixels, right? And you have this, okay, there's 2 pixels, now we're going to turn that into 4 pixels. Your whole screen's made up of 4 pixels. Okay, so you have this pixel, which is orange. You have this pixel, which is blue. You have this pixel, which is, oh, well, no, don't worry about that yet. So we have the shape of our triangle trying to be drawn. Right there. Sorry, I totally ruined the example. Oh boy. Right there. Right there. So you have this triangle trying to be drawn, okay? But say you have another triangle that is just, I don't know, sitting right here, okay? So say you wanted to draw another triangle right there. Well, you see that right now, the way we have it is it just depends on the rendering order. So which way did we pass it into the GPU? There's no way for us to tell which one to order first. So say we drew this one first, this one was drawn first, and then this one was drawn second, and it just overlapped what the hell else had already been drawn. So that's how the system works right now. I'm gonna turn this into here, and then I'm gonna go here, and then I'm gonna make it so it looks a little bit easier to read. So this is the second drawn, and this was the first drawn. So say we did draw this first, did draw this second, but we wanted this to appear behind this guy. Well, what there's something called a Z buffer. Z buffer. And what the Z buffer does is you send it through the command encoder, and the command encoder will then say, okay, well, so I drew this one, so this one actually got drawn first now. So say we draw this one first, and we want it to appear, no, screw it. This one was drawn first. This one was drawn second. So say we want this one, though, to appear in front of this one. Even though it was drawn first, we want it to appear. Well, we'd give it a Z, right? We give it the depth, the Z behind this one of a lower number. So if we say your nose is 0 and then it goes out to infinity, well, we want the lower number of a Z to render first, and then the higher number. So we'd set this Z equal to something like 0, or well, let's just say Z equals to 2. And then we'd set the Z of this green one equal to 3. So now we have depth. It goes along the Z axis from 0 out to infinity, and we know that this Z has 2 and this Z has 3, so we're going to render this one second because the Z is higher. This is called the less function. So we're drawing the thing that has a lower Z value. And yes, so let's implement that, the Z buffer. There's a couple things we're going to need to do. First being the metal view needs to have a depth pixel format. So let's do that right here. Self.depth stencil pixel format equals .depth 32. We want 32 float, and then we're also going to need to do that on the, let's go to the primitive. We're also going to need to do that on our render pipeline descriptor. So render pipeline descriptor dot depth equals dot same thing, depth 32 float. Just start typing depth and it comes up. So we've now given it the depth, and so yeah, that should do it, right? We should have depth. We should know which one to draw first. Well, not exactly, not yet. Let's add 2 triangles to the scene so that we can see, and let's stop rotating. We're gonna add 2 triangles. We're going to scale. I'll add all this stuff later. I'm going to delete it for now, and we're going to call this T1 to have 2 triangles. We're going to go back to having the other triangle. This doesn't need to be there, but I'm going to keep it. And then, so T1.scale, this will be the T1. We're going to create a second triangle to kind of talk about that Z buffer and just make sure it's working. So T2, we're going to instantiate T2, and that color is going to be not red, but we'll make it green. We can init, we'll scale, so T1 will be scaled by 0.8 just like before, and then we'll do T2 times scale it by 0.5, so it's smaller inside. And we have to, as of right now, we have to draw it first, and we're also gonna translate it. So T2 dot rotate translate scale. So we need to do translate rotate scale, right? Is that what I said before? So translate rotate scale, translate rotate scale. So we go scale, and then so that'll be the last thing we do, but we're gonna go T2 dot translate float 3, just a little bit over, so we're gonna go -0.5, 0, 0. So we're just gonna go over 0.5, and let's just kind of see. Oh, we didn't add it. I'm gonna add it to the scene, and we're gonna do it second. Probably should do it first. I'm probably gonna do it first. Let's see what comes up. Okay, yes. So I drew it second, and you'll see that the rendering order matters. So if I were to switch the way in which I added these to the list, so we see green's in front, red's behind, but if I just kind of change this, you'll see that remember, green was in front, red was behind, and now red is in front, green is behind. But there's no way for me to change that. What if I wanted the green to be in front? So I'm gonna keep it like that, because now we're gonna want the green to come to the front instead of being behind. And so what we're gonna do is use that Z buffer. We haven't actually used it. We've just said that it exists, but we haven't used it. We also need to create something for the called the depth stencil descriptor. And if I go here to the Metal Programming Guide, shows me all this cool stuff. Go to the organization execution model. See, we have this depth stencil state that we'll need to put into the render command encoder. So it's the exact same thing as our render pipeline states. Like we set our render pipeline state, we'll need to set a depth stencil state for the command encoder to then use for the Z. So let's do that too. So we've said what the pixel format is. Now let's set it. So we got to go to our primitive. And right here, we're doing our vertex descriptor stuff. That's cool. But we're now going to need something called var depth stencil state. MTL depth stencil state. Just like so. And so let's create this depth stencil state. Vertex descriptor, we're just gonna go build depth stencil state, pass it the device, and we're gonna put it under here. So func build depth stencil state, device, MTL device. And this is where we're going to do our depth stencil state. So depth stencil state, so just like we did the render pipeline descriptor, for the pipeline state, we're going to need a depth stencil descriptor. So let depth stencil descriptor equal MTL depth stencil descriptor. We're going to set a few properties on this depth stencil descriptor. Okay, so there's a few things that come up. Is depth red enabled? Well, obviously we're gonna want to start doing some depth stuff. Depth stencil descriptor dot. So there's something called the depth compare function. So this is what we're gonna call for dot less equals dot. Well, we can do always, greater, greater or equal, less than or equal, never. Just which Z buffer do you want to draw first? Well, in our case, we want to do the one that has the lowest Z draws first, so it's going to go dot less. And then we're just going to say depth stencil state equals device dot make depth stencil state, and use that depth stencil descriptor. So now we have our depth stencil state, and just like in that image that I showed you before, we're going to want to set it in the rendering command encoder every single time down here. So we're going to say command encoder dot set depth stencil state to our depth stencil state. Okay, cool, huh? So now let's go ahead and press play and see what happens. Remember, our green was being drawn behind. We now want to be drawing it in front. Okay, green is now in front. So, but how the hell did that happen? What are you talking about? If we go back to our scene and we go, let's just kind of comment this. So this is our red triangle. This is our green triangle. And we notice that we draw T2 first, which is our green, and then our T1, which is our red. Technically, we don't translate in Z at all. We don't give it a Z, a difference in Z. No, but yeah. So green is first. Red is second. Red should be in front of that. But when we do this, actually now I'm kind of confused. It's kind of crazy. I'm trying to think. So maybe it's when I do the translate of the T2. It goes to maybe 0. Maybe it starts at -1, huh? So let's translate T1. Let's go float 3 and the 0, 0, 0. So we're gonna go float 3 and I don't know, 0.3 direction, and see if, and this would be 0.4. Let's see if now that we've given it a Z translation that it actually works. Let's see. So yep. So look, so now our red is being, so we've translated it back by the Z. So our T1, which is red, has a lower Z value than the T2.translate, which has this. So if I were to set this to 0.2, we should now see the green is drawing in front. So we've given it a depth buffer. We've literally put them in like sort of 3D state, but they're not really in 3D state. They're still being drawn in 2 dimensions. And like if I were to set this to go back to -100, you know, way off and who knows where, I don't even think it's going to show up, because really we still have clipping space that we need to take into consideration. It won't even show up. You see, like there's no 3-dimensional space. It's just from 0 to 1 which shows up first. So if this was 0.999, it will show up, but our clipping space goes from 0 to 1. So anything, so this will show up. It won't look like it's far away. It won't look like anything. But once we set this to 1, well, our clipping space is limited to 1. So it might actually show up. 1.01 might not show up. I don't think it's going to show up. And yes, disappears. So we have depth for the Z, but we don't actually have depth for 3 dimensions, if that makes sense. So let's do that. Let's talk about depth for 3 dimensions. Okay. So in order to talk about depth for 3 dimensions, we're going to need to pull up our drawing because I have more on here. Okay, we've talked about this, the rotation, the scaling, but we haven't talked about how to make it look, to give it, you know, space in the real world. So let's zoom in on this. There are 2 types. So projection. When you think this is perspective, projection. That's weird. Projection. Orthograph. Oh my God. My computer is gonna have a heart attack. Chill, bro. All right, so sorry, I'm just gonna undo this or erase it. Just having a hard time. All right, so we have perspective projection and we have orthographic projection. And when you think of projection, literally think of a projector projecting onto a wall. You'll notice in both of these images, there's 2 types of them. 2 types, projector. You'll see that there's this front screen, and this near clip plane is basically what's going to get drawn on your screen. Okay, and this right here, this little view with the balls, that is your screen. And when we're projecting it into 3-dimensional space, you know, there's something called the vanishing point. And so when you have a picture of, I like to use this whenever I do explanations of the projection. You have a train track that goes off into the distance, and there's this vanishing point. It goes off into infinity, and then the vanishing point, these lines are eventually like going to go off and touch. If it was far off in the distance enough, those lines would then go and touch. And so what these two different perspective and what these two projections do is they do different things. So the orthographic is going to maintain these parallel lines, and it's just going to stay the same no matter how far back they go. Like you can put this to -100, it will show up behind it, but it will be the same size. It won't have this vanishing point. Whereas if you go over to the perspective projection, this is more perspective. This is more realistic. This is kind of how your eyes view the scene. So you'll see that off in the distance, this ball's way back here, so it's going to show up smaller. Where this does show up behind it, but it's not smaller. It doesn't represent realism as well as this one might. And so what I like to do is I like to do the perspective first, and then orthographic kind of comes later, because I don't really care too much about orthographic as of right now. I just like to see the perspective and kind of for our learning purposes. That's so weird. All right, I'm gonna do this. So you see we have top left, bottom right, and we have our near and far. So this right here, so you see this little ball out here? This ball was rendered to. This ball has vertices. This ball has all sorts of data associated with it. But since it falls outside of these boundaries, right, top, bottom, and left, we are not going to draw it. The clipping space will eliminate it, and it won't be drawn. And if part of this ball was in, it would only draw part of the vertices and not draw the outside. So that's kind of how this is going to work. That's what these are. These are these planes for the left, right, top. But then we have the near plane and the far plane. So what you can do is if this were like a line coming all the way through, and then your X and Y. So this is the Z. Treat this as Z, and this was negative Z goes off into the distance. Z goes towards your face. Z comes out and pokes you in the nose. If this was negative Z out here, then the far clipping plane, you could put this wherever you want. You could put this at negative infinity. You would be drawing a lot. So realistically, you'd only want to put it maybe to like -100. Sorry, my computer's being kind of slow. I'm going to just run a little clean on it and let it do its thing. So it'll be up here doing its clean. So that's kind of how it works. So this is the far clipping plane, which would be 100. Anything over 100 would now not be drawn. And anything at our near clipping plane, so we'll put this like 0.1, will be drawn. So from 0.1 to 100, everything will be drawn. Remember how we did 100 in our X code and it didn't draw? Well, now we're going to set our far plane to 100, and then it's going to just kind of take this Z value, and really it's the W value of our homogeneous coordinates that it uses to determine the size of it, but it'll just make it look farther off in the distance rather than the same size going all the way back into 100. So let's do it. This is train tracks, by the way. I didn't finish my train tracks. Man, my computer's running slow. That's okay. No thanks. Memory clean. Now we have 3.6 gigs of memory available. All right, so let's do that. Are we ready, kids? Aye, aye. I'm gonna get sued for saying that. I'm gonna actually delete this temp scene. I don't even need it anymore. I don't even know why it's still here. Yeah, so let's do that. Let's go into our mass and let's start. Let's do this. So we have our scale, rotate, translate, but the projection matrix is a little bit different. If you noticed that in our drawing, not this drawing, or the drawing, which I might have, nope. You'll notice that we have our camera here, right? So we'll create a camera. This camera has its own matrix applied to it, and I'll probably do that in the next episode. I won't do that in this. But this is like your eye. This is your eyeball. That's a terrible eyeball. Whatever. This is your eyeball, and it's looking here. So your camera is at 0 right now. Z of 0. Point 1 is right in front of your face. Yes, so this is right in front of your face. So if you look at this, everything that's in here is the scene, right? So this is viewing the scene. This isn't model. This isn't messing with the models. This is applying all the models. This is creating a matrix that all the models will be multiplied by. Remember how we were moving, say, this vertice and this vertice and this vertice and this vertice together with a triangle? Well, now we'll be moving all these vertices with other vertices in the scene. So we're going to want to apply this projection on everything in the scene and move it all together. I think it's a fine transformation is what this is called. But everything in the scene will move, so we're not going to pass it in as model constants. We're going to pass it in as scene constants. So the projection matrix basically takes in a few fields. Let me bring up the projection matrix function because I have it right here. Nice. I'll just put this off to the side. I'll probably put it in the middle of the screen. Right there, and then I'm going to put you right there. And right there. So to make our projection, we're going to, instead of making it do a function, all this stuff, our perspective is going to stay the same unless we change it, but it's going to be applied to it. So let's do that. Oh boy. Here we go. So in it, we're gonna, instead of like making a function, we're just gonna initialize a projection matrix. It's gonna basically be an override kind of a deal. But this will take in a field of view being in this image, the field of view would be kind of like this to this line to this line to this line. And so this will come at an angle because it's which angle I can't remember exactly why it's an angle, but that's what it is. The field of view is what shows up, like zoomed or far. I know 90 would be like extremely zoomed in, and 35 would be far away, but that's what the field of view, which is in radians, will be. And then our aspect ratio is the screen size, so the width by the height, that's our aspect ratio. The near Z and far Z, and what the aspect ratio does, it determines these clipping planes for the top left, bottom right. And yes, so let's do that. Let's see. Now we have a near Z and far Z. We already went over that. Let's do it. I just want to do it now. I'm excited. So the field of view is going to be a float. The aspect ratio is going to be a float. The near Z is also going to be a float. Far Z, float. Okay, so just like we did before, let's do this stuff. This is going to be in radians, so I'll actually take, I'll turn it into radians. I can take it in as degrees and then convert it to radians, or I can do that. What are you complaining about, dude? Okay, I can convert it to radians here, and what I'll do is I'll just create a little function outside of here. Var pi as a float. We can say double. We'll say a float equals. You can. Oh wait, let constant. I think it's like let constant. Let pi equal. And I think if you go option P, you get pi. See that? But what's going on? Unresolved, let pi float. I can't remember how to make it constant, so it just stays like that. We'll just use pi in there. So I'm going to create this function called radians, because we're going to want to convert this to radians from degrees. So radians from degrees, and then take in degrees, which will be a float, and then we will just return degrees divided by 180 times double dot pi. And that needs to be a float. I believe. Will this work? It's time to double. I don't think it will. I think it's going to throw an error. Looks okay. Yep, it's going to say go to hell. So float double. I think that should do it. Cool. So now we can do radians and just say FOV equals radians of from degrees FOV. See that? So now I just did a quick conversion right there. The aspect ratio, we find all this stuff doesn't need to be converted. We just need to convert whatever degrees we pass in to let degrees FOV. Is that better? Is everybody happy? This will be degrees FOV, and this will be just FOV. Okay, so now we're gonna use this function. So you see how y, I'm just gonna kind of call these things stuff. So like let x equal, it'll be y divided by aspect ratio, but I don't have y yet, so I have to create y first. Y equal 1 divided by the tangent of the field of view times 0.5, and then z, let z equal far z divided by near z minus far z, and I'll call this let z2, call that z1. I'm probably gonna z2 equal z1 times near z. Okay, and see how this is kind of in homogeneous coordinates. See that? This is the x, y, z. This is like w. We'll call this w because it's in homogeneous coordinates. What it's gonna do is go into the rasterizer, and it's gonna divide by this value that outputs, and it's gonna get smaller as it goes off into the distance. This is where that perspective, this is where it gets awesome. So, because if you look at this one, it uses the homogeneous here, but it doesn't actually manipulate the this value, whereas this one turns it into a 0. It's pretty fascinating. There's a lot more behind it. I'm not going to describe it. I'm just going to implement it. And then this is degrees FOV. Okay, so now let's just put that in. Columns equals, see, since it's initialized, we don't need to create a result. We can just say columns equals, and then we can say float 4, and, oh, well, probably wrap it, huh? Float 4, 1. So we'll go 1, 1, 1, 1. No, well, zeros. Let's do zeros because there's more 0. Why would I do? Yep, and one more 0. So it's a float 4. We're just going to copy that. Comma, comma. All right, so this will be x. This will be y. This will be z1. This will be z2. And then don't forget that -1 right here. And we have it. Let's make this look just a little bit prettier. I should have done this before. There. Oh, you probably need a comma. Something's missing. No, this is fine. Okay. What's going on? Z2. Oh, we called it W. This needs to be columns. And yeah, so now we've set our columns to be exactly what, you know, we've done up here with these values, and we should output our Goish projection. So now that we have our projection matrix, let's apply it to the scene. And just like I said before, where with our primitive that have their model constants, right here, we're going to need to set the scene constants. So every scene should have scene constants. So let's create some scene constants. We're going to copy the model constants, create some scene constants, and this is going to be the projection matrix. Projection matrix equals the same thing. So actually, let me go back to my math and make sure I call it perspective. So we got perspective, and then we're going to call it FOV. We'll take in degrees FOV, just like so. Perspective degrees FOV. And then in our scene, we're gonna need to do exactly what this does. We're gonna need to take this. I'm gonna leave it though. Put it in our scene, because now we're gonna need to apply some scene constants to our command encoder. So we have our device, but we need var scene constants, which will be equals scene constants, and then we'll need to, so those are instantiated. That's kind of cool. Now we can say scene constants dot projection matrix equals, well, we can just create one. So we go matrix float matrix float 4x4, and there's an initializer now that's over that we can use called perspective degrees FOV. So we're gonna pass in I don't know, 45. Aspect ratio, we'll just do 1 for now, 1/1 with the 1 you know what I'm saying. Near Z will be 0.1 like I said, and then far Z will be 100 away. So that's that. Rid of this. So that's that. Now let's just throw these scene constants into the command encoder. So command encoder dot set vertex bytes. We're going to pass in the reference to the scene, just like before. Scene constants. The length is going to be memory layout of scene constants dot stride. And let's see where we're going to put it. Let's go to our shaders class. Model constants at 1, we'll put it at 2. And yeah, cool. So that's that. Let's go to our, so it's gonna set that every single time on the scene, and bada boom. Let's see, let's go to our shader class. Basically the same exact thing, so we'll copy that, put a comma, and go down. Do scene constants, but we need the struct, so we're going to copy. This will be scene constants. This will be scene. No, that's not what I meant. Scene constants, and this will be projection matrix. scene constants and scene constants, but that needs to be lowercase. Buffer2, like I said, will be a buffer2 now. And so now that we have our projection matrix, we could just say projection matrix equals scene constants dot projection matrix times that. Now let's press play and see what happens. Nothing. Why does nothing happen? It actually deleted everything. Well, that's because right now all of our objects in our basic scene lie on 0.4. Like, they can't see it. So and it's also positive. Our z goes back to -100. So we got to put this at like -5, and then we'll put this at -6. This would be like -2, and so let's see what happens here. Yeah, so you see how it goes off. Let me move this in just a little bit more. So this is not -2, this will be -1. Remember, it's crazy zoomed in right now. 40. So let me see. Okay, so you see we have this guy's in front, this guy's in back, and you see how he's going back a little bit farther. Now let's go off maybe 20. So the green one will be -20 away. It'll be way off in the distance, kind of on the horizon. And you'll see now he is back. I mean, I don't even see him. He got small, quick. So let's just say like -10. -10. It's very negative. It's positive. It's so negative, it's positive. And see, he got way back there, and this one stays in the same spot right in front of you. But now that he keeps moving back, the reason was because and now if we wanted to move the red triangle back, we could just go like -15 for the negative, to push it back towards the negative more for the red triangle, and the red will be behind the green and in front. So we're using the Z buffer, we're using all this stuff, and the red won't. It is behind. Not lying. So the green, we're not going to translate it -1. We're going to go just 0. We're going to go -0.4. Just a little. Not 0.04 either. That'd be nothing. We're just going to kind of move it over, shift it over. And let's see what we get. Show you that the red should be behind the green. And yeah, see how we're just moving them back off in the distance. Something cool also, let's get rid of this T2. We don't need it anymore. We just need the T1 for example purposes for now. Don't need T2. T2.scale. We don't need to do any of this stuff. Oh well, we will do T1.scale. We don't need to add the child T2. But now that we have T1 scaled, let's go back here and let's go T1.rotate. Angle would be delta time, and we're going to rotate around the x-axis. Remember, it was kind of cutting itself off at the half, but now I'm going to do 0, 0, 0 around the x-axis, x, y, z, and instead of cutting itself off, we should now see, oh, it's way off in the distance still. That's okay. Doesn't cut itself off. It's literally rotating around that axis way out there. And I'm going to bring it in just a little closer. We'll just go to -4. Way off in the distance, but -4. And now it's rotating around this axis and showing everything because it's now projected into space. It can project this vertice back. It's going to that vanishing point, making it smaller in the distance, and you get this triangle. The next thing I want to do to kind of end this episode, let me see where I'm at, 114, is I'm going to make a cube. And yeah, so give me 1 second. I'm going to grab my notebook that I have my cube written down in. I didn't actually write this out. I just want to do it because now that we're rendering in 3 dimensions, it'd be kind of cool to have a cube. So I have this cube diagram that I drew out because I want to, I recommend you go and try to put together what a cube would look like, make your own, because there's so many different ways. We're going to create a new node right here, new file called cube. So cube, create it. It's going to be just like the triangle, except it's going to have more. Since we're working in 3D now, we can do this. So we're going to make this cube. Cube will be a primitive, same thing. The color, don't worry about the color of the cube. We'll make our own colors. Don't worry about this color. We won't do this init for the cube. That's ridiculous. Build vertices. So the vertices, I'm just going to kind of copy exactly what I have right here. So a cube is made up of 7 vertices. So we're going to go right here. We're just going to copy this twice, 3 times, eliminate this last one. This color actually needs to be float. Whoa. Float. I wish I knew how to spell. And then this is going to be 1, 0, 0, 1. And then I'll just copy this all the way down and I'll make different colors. Oh, wow. So we're going to make them all different colors for the vertices so that it comes out a little different looking. I'll start with RGB. Then I'll go that, then maybe 0.5, 0.5, 1, 0.5, 0.5. All right, so I don't know what those are going to actually look like, but we now have our vertices, which need commas. We'll make this look a little bit nicer too. So we got you can probably fast forward if you want. I'm not going to. I'm going to show you the exact. I was going to like pause it, but no. All right, so our first vertex is going to be at, this is -1, -1, +1, +1, negative, positive, negative, positive. Okay, so there's our x's. 1, -1, 1, 1, -1, 1, -1. 1, 1, negative. 1, 1, -1, -1. And then let's do our z because now we're using 3 dimensions. This is just 1, 1, 1, 1. Odds are, if you make your own cube, it's kind of cool, is that, I mean, nobody's probably ever made a cube just like that. There's so many different combinations for making a cube because when you look at this, I did mine from 2 to 1. You can do 0 to 3. You can do 3 to 0, 1 to 2, or you can do, draw the back first, the top first, the front. There's so many different combinations that you can basically almost create your own cube that no one else has drawn before. I don't know if no one has ever done it, but I mean, statistically, if you do it by yourself, then yeah. So that's why I kind of did it, and I wanted to create my own cube that no one's ever done before. So I'm going to just go like this. I'm just going to type them out, and I'll put the commas in afterwards. This goes kind of along. So 0, 1, 2, 2, 1, 3, 5, 2, 3, 4. Well, let's not do it on the same line. Let's go 0, 1, 2, 2, 1, 3. And I'll go like that. And I go 5, 2, 3, 5, 3, 7, 0, 2, 4, Okay, so now that I've done that, I like to go like this. That's the front square, 537. Oh gosh. This is the right, top, left, back, okay, so now there's that. Now we're gonna need to go put my commas in. Okay, so now there's these guys. I like to also point out what these are. This is triangle 1. Probably triangle 2. So every square is made up of 2 triangles. So this is the front square, the right square, and you're just positioning them in space in 3 dimensions. And in our basic scene, I hope these are right. I haven't, this is, like I did this in front of you. So instead of doing a triangle, we're going to turn all these into a cube. We're not passing in the color anymore. Remember, I eliminated that color, so let's go right there. Cube, t1.translate. These can do exactly the same thing. And since I'll put C, 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 C. And if I press play now, oh, let's do C2. All right, so now stop that build. Build this one. Stop that build. Let's go. Let's see, we have a cube now rendering, doing its own thing. Oh boy. See that? Now let's not just rotate around that. Let's rotate. You have to do rotate on the different axes. So you'd have to do like this. And then instead of that, you'll have to do that. You can't do it all together. It comes out looking funky. You have to do each axis individually, rotation-wise. And boom! Oh boy! We are now in 3D, people. Keep your seats back in locked position. It's 3D time. Oh yeah, and look at it just nicely rotate around that 0 right there. Yeah, so that's it today. We've gotten to 3D. That's pretty cool looking. If you guys liked this, let me know. If you have any suggestions on how I should do this in the future, let me know. But yeah, and we're now in 3 dimensions. Another cool thing we can do is, so you saw how it was filled, but if you go back to our renderer, and right before we do this, we do the render of the scene. Let's just type command encoder dot triangle fill mode, set triangle fill mode. Just do dot lines, and we can do just the skeleton of our cube, and you'll see that we have just that. Look at that. That's so cool looking. That is so freaking awesome. Okay, so that is our triangle doing triangular things. Yeah, let's just set it back. That's just something you can do. I'm going to set it back for the next episode. But, yeah. Yeah, let's play it. One more time. This is where we're at. That wasn't so hard. Yes. So now that we have that, that is the final result. And yeah, 2 out.